Okay, so we're going to be going over 6.3 today. It's exponential functions. I have the Desmos just scientific calculator pulled up, not the graphing calculator, because our first problem asked us to use a calculator to approximate, and I don't have my TI with me, but even if I have my TI, you wouldn't be able to see it, so I'm going to use our Desmos scientific one. I know HonorLock gives you a scientific calculator to use. So let's go ahead and do this. So when we're typing in, it's 130 e to the 0.048 times 8. Actually, a similar question because that's the one I did. I did this one previously, and I didn't feel that I went into enough detail, so I wanted to do a better video. That's why it says they're all answered. Okay, so I typed 121 in. Now I'm going to get my e. That e is the natural number, so I went to functions on this calculator and then e to the x. The x, it's going to allow me to type in our numbers, so now then I'm going to go back to main, 0.025, and then exactly how I see it, parenthesis, 6, parenthesis. Whenever I'm typing something into the calculator, I try and type it exactly how I see it, so that's exactly how they gave it to us. If you can type it in exactly how you see it, you're not going to have less likely for human error. Because I could have went ahead and multiplied these numbers in the exponent and put that in there. But if I can type it in exactly how I see it, I'm less likely to make a simple mistake. So let's see. Round to 3 decimal places, so 140 point. We have 5819, so it's going to be 582. And I'm going to put away our calculator for a little bit. Determine whether the function given in the table is linear, exponential, or neither. If the function is linear, find the linear model. If it's exponential, find the exponential model. Okay, so when we look at these, linear ones are our straight lines, so they're going to change the same each time between our x values. So our x values here, it's going up by 1. That's a pattern, so that's good. Over here, 6 to 11 is 5. 11 to 22 is 11. 22 to 33 is 11. 33 to 55 is 22. So if it was exponential, you're going to see it go like, let's say it was 2, so it'd go 2, 4, 8, 16, 32, 64, so on and so forth. It's going to change by that exponential jump. It's going to double or triple each time, or more. It doesn't just have to be those. Linear changes by the same thing each time. So since this was 1, this one was 5, 11, 11, 22, this model is neither because it doesn't have that pattern that you can see. Okay, similar question. This one is our exponential, and it's a basic exponential one, but let's talk about this a little bit. So we have -1, 0, 1, 2, 3. Then we have 1/4, 1, 4, 16, 64. When I'm looking at exponential functions, I remember my exponent rules. That's the first thing that comes to my head. I'm trying not to leave anything out that I did last time. So whenever we have anything whatsoever raised to the 0 power, it's 1. Regardless of what it is. I used 4 this time. If it was x, y, z, and all of that was raised to the 0 power, it would still be 1. So anything to the 0 power is 1. So if we're using this exponential function model, and at 0 it's 1, that's a sign that whatever you're using is, I'm trying to think of the correct terminology to use, but if whatever at 0 is 1, that tells me that whatever 1 is my base. So at 1 I have 4, so my base is going to be 4. X is my unknown. This is my y value. So f of x equals 4x is my function. I know this because if I put 0 in, I'm going to get 1. If I put 1 in, I get 4. 4 squared is 16. 4 cubed is 64. Remember negative exponents from our exponent rules? If I have anything to the negative power, it changes it to be on the bottom. So if I had 4 to the negative 2, that's going to be 1 over 4 squared, which gives us 1/16. This stuff is important too because when we graph these later on, you need to know this. I feel like I need to tell you something else about this. Be sure this one is linear, so ours was exponential. So I'm going to put 4 to the x. When we're doing these graphs, x is going to be our variable. Get us a new one. But so we have at 0, it's 13. Well, I guess first we have to determine if it's linear or exponential. So -1, 0, 1, 2, 3, 13 over 12, 13, 156, 1,872, 22,464. This is exponential if you've ever seen it because it grows that exponentially each time. So the next thing we have to figure out is what is the exponents we're using. So I always look at 0. So at 0 I have 13. Anything to the 0 power is 1. So since I have that 13 there, I don't want to. For it to be 13, it's going to be something to the 0 power because this is going to be, I shouldn't put 0 there. It's going to be, I shouldn't put x there because x is technically that. So let's use n. Something times n to the 0, where n is going to be our number. So 13n to the 0 is going to give us 13 because this is 1. So I'm going to have 13 times something. Now what that something is given away by my negative, because remember anything raised to the negative power, like 4 to the -1 gave us 1/4. So let's just say I had 13 times 4 to the -1 would give me this 1/4, and then it'd be times 13. So it's going to give me that 13 over 4. So when I look at my negative, I have this 12. This doesn't pertain to this problem specifically. This is an example. So when I look at this one and I have 13 over 12, that tells me that my n is 12. That's going to go in here. So I'm going to have 13 times 12 to the x power. And that's exponential, so that's what we're going to put right here. And we can check this as well. So if I had 12 to the first power is going to be 12, and then 12 times 13 is going to be 156. 12 squared would be 144. I assume 144 times 13 is 1,872. So let's type this in. And then your exponent's going to be x. Thought I got fat fingered there for a second and hit more buttons. Okay, similar question. This part is one that I really wanted to talk on more. I'm going to go ahead and pull up the exponential graph. So when you're graphing these, it's just like our transformation ones in 3.5 and 4.3. It doesn't matter if you find a certain point, it's going to put you back down at that 0. So your exponential graph, you can click on it and it's going to tell you exponential tool. Logarithm is the next lesson. Real quick while we're looking at them, exponential graphs and logarithm graphs, they're inverses of each other. So like x squared and the square root of x, adding and subtracting, multiplying and dividing, they're inverses of each other. So our exponential tool, go ahead and just click anywhere because it doesn't matter. It's going to pop it up at 0, 0. So if you find a certain point, you've wasted your time. Okay, our graph that we're graphing is 7, I'm going to have to redo it now, x minus 1. So can I click on it? Beautiful. Our base, when we're doing exponential, our base is this big number. Whatever being raised to the exponent, our base is this. And that's important for when we do our logarithms because your base is still the same between them. It's just how we write them. So our base is 7. They already have that loaded in here. Then it's x minus 1. So if you remember our transformations from back when, if it's with x, it's left and right, and it's the opposite of what you think. So since ours is subtract 1, that's actually going to be right 1. And right is a horizontal shift. So we're going to go right. Can I do it? It's not moving. 1. So, and we didn't have to do anything with our 7 because they already had it put in there for the base. Okay. What is your domain? So our domain is unrestricted on these because it goes all the way down to the negatives. It's never going to be less than 0 though, unless we have a graph that moves it, like a transformation that moves it down. Because when we have it to that negative exponent, it's just making it smaller and smaller fractions. Positive exponents, it just keeps going and going and going. It's just going to be really, really big numbers. So our domain on these is negative infinity to infinity on all of them. And that's going to be reversed when we get to our logarithms, because remember, logarithms are inverses of exponential graphs. I hit an extra button. Oh, and then our range, like I said, unless there's a transformation that moves this down or up, it's 0 to infinity with a parenthesis because we're not going to equal 0. Determine the horizontal asymptote. Our horizontal asymptote is going to be y equals 0. Because our graph doesn't go below that at 0, so y equals 0 is the understood horizontal asymptote. Our y-intercept, so if we want to find our y-intercept, we can put 0 in for x. That's probably going to be the easiest. So y equals 7 to the 0 minus 1. So we're going to have y equals 7 to the negative 1 power. Can't see that good. How do I want to do this? Which, anything to that negative 1 power, it makes it 1 over 7. And you could use a calculator on that if you wanted to. Oh, my nose. Goodness. Okay. Next. Similar question. Okay. So we're going to click to enlarge our graph. It's an exponential graph, so we're just going to okay. Since it's to this 1/4 base, I was like, did I click the logarithm graph? Since it's to 1/4, it's going to make it smaller this way. It's, yeah. And then we have that 5 times 1/4 to the x, so and let's make sure there's nothing else going on there. So 5 times 1/4 to the x power. Our base is 1/4. It's 5 times that. When we have 5 times our normal one, that's going to be a stretch. And that 5, since it's times everything, it's vertical. Okay, domain negative infinity to infinity. Because there's nothing that's restricting it. Just remember that this is going to change. Well, it's not going to change on our exponential graphs. But our logarithm graphs are opposites. So the range will be negative infinity to infinity. What is the range of this? It's going to go from 0 to infinity. Even though the graph is backwards, that does not change our range. It starts at 0 and goes to positive infinity. Then at horizontal asymptote, same thing, y equals 0. That'll change if our graph is shifted by a vertical. What is the y-intercept? So when we find our y-intercept, we can do 5 times 1/4, and we're putting 0 in for x when we're solving for our y-intercept. Anything to the 0 power is 1, so I'm going to have 5 times 1, which gives us 5. I just want an integer. Cool, next problem. Click to enlarge. Exponential tool, click wherever because it's going to pop up. And then we have our base is this 2 because it's whatever is being raised to the exponent. So our base is 2. Since this is x divided by 2, that's going to go with our horizontal. If there's something that's right there that's being multiplied or divided by that x as the exponent, you're going to do horizontal. If it's on the outside, it's vertical. If it's with x, it's horizontal. So if it's multiplying and dividing, it's stretch or compression. If it's add or subtract, it's shift. And that's the same with the vertical. It's just the whole thing, not just x. So since it's x over 2, I'm going to do \2 here to get that compression. And then that 4 plus is going to mean our graph is going up 4. They just put it in front of it compared to behind it. So that 4 plus is up 4. Okay. Domain is negative infinity to infinity on exponential graphs. Then our range, this is one of them, so we've shifted our graph up 4, so it's going to be 4 to infinity, not 0 like the other ones. And then our horizontal asymptote is going to be at y equals 4 now because we moved our graph up 4. And then our y-intercept, when we find this, we're still going to put 0 in for x, so it's going to be y equals 4 plus 2, and then 0 divided by 2. 0 divided by anything is still 0, so this is going to be anything raised to the 0 power is 1. So I'm going to have 4 plus 1 equals 5. Similar question. Click to enlarge. E to the x plus 4. So this one, they just give us the exponential tool. Click wherever, it's going to put it there. Our base is that e, and then we have to the x plus 4. Since it's with x, that's going to be a horizontal shift. When it's plus 4, though, it's always opposite. So we're going to go left 4. So our horizontal shift is going to go to negative 4. Okay, save, check answer. Domain of exponential, negative infinity to infinity. Our range, it starts at 0 and goes to positive infinity. Our horizontal asymptote, this one has y equals, just put 0. Oh, and that was it. Oh, wait. Similar question. Negative 14 to the negative e to the negative x. Okay, so negative 14 minus e. X. When we do this, they already have the e as the base. Since I have a negative with my e, since it's subtract e, that's going to be a reflection. Woo-hoo. Come back here. I'm going to have to sit over here and talk. Okay. So, since I have a negative with my e and a negative with my x, I'm going to have to reflect over both of these. Because this negative reflects it across the x-axis, this negative reflects it across the y-axis. So, negative's on. Negative 14 here is down 14. That's why if you look at the scale on this graph, there's so many. So, negative 14. Okay, save. Domain is still negative infinity to infinity. Our range on this one is going to be different because it has been flipped. So it's going to go from negative infinity to negative 14 because we have a negative. So negative infinity, because always least to greatest, to negative 14. And then our horizontal asymptote, they have y equals on this, so I just put negative 14. Similar question. This one has a double negative as well. So exponential graph, click wherever. So I have a negative e and a negative x minus 2. I'm going to go ahead and write it bigger so you can see it. 6 subtract e. So click back on this. I know I can't do this up here. But I have a negative here and here. So once again, it's going to reflect both. Please let me click you. Yes. And then this 6 out front is a positive 6. Since it's positive, that's vertical because it's outside as well. So it's going to vertically shift up 6. And then that divided by 2 goes with our horizontal stretch compression. Since it's divided by 2, I'm going to do backslash 2. Save. Check. Then domain's negative infinity to infinity. Range is going to go from negative infinity to 6 because this one is also reflected. And that means our horizontal asymptote is at y equals 6, and we just have to type 6 because they have the y equals. I like these. No graph, y'all. Similar question. This one is just the basic rule. So whenever I have two bases that are the same, they're saying that we can get rid of the bases and put the exponents equal to each other. So here, I'm going to have x equals 6. If your bases are the same, we can go ahead and look at our exponents. And this is just the super basic rule, and just put 6 into the solution set so that we can do these problems. Oh, similar question. So 4 to the negative x equals 256. So I need to figure out if 4 goes into 256. And my calculator should still be pulled up right here. So what I'm going to do is clear that. So I want to know if 4 goes into 256. So I'm going to do 4 times 4 times 4 times 4, and that's 256. So 4 to the 4th power, because there's 4 of them, is going to be 256. So 4 to the 4th power equals 256. I'm going to use this, so let's minimize that, equals this 256. So now then, instead of 256 here, I'm going to put 4 to the 4th power. So I'm going to have 4 to the negative x equals 4 to the 4th power. Now then, since my bases are the same, I can say negative x equals 4. And this is going everywhere and not in the flow. Now, I can't have negative x equals 4. We have to move our negatives, so we can divide by a negative. Negative divided by a negative is a positive. Positive divided by a negative makes this negative 4. There is a lot of rules to this final test, so be sure you print out the paper that has the rules on it that I've made. You don't have to use mine though, you can find a different one. I just know I have them available if you need them. Okay. So I'm going to write it over here for when I pull the calculator up now. 4 over 3 x power equals 64 over 27. All right. So since 4 and 3 are like the bottom, we're gonna see 4 to what power is 64? 4 times 4 times 4. It's gonna be 64, so we're gonna remember that. And then 3 times 3 times 3 is gonna give us that 27. So both of these to the third power is this. So I'm gonna go ahead and third power x equals, and this is gonna be 4 thirds to the third power, which means x equals 3. Okay, last problem. We have 49 x equals 36. What does 7x equal? So I know that 49 is 7 squared. So what I want to do here is be 7 squared x. I know 36 is 6 squared here. So if I just need to solve it for 7x. Okay. So I'm going to go ahead and simplify this. The exponent rule here is you multiply them. So I'm going to have 7 to the 2x equals 6 squared. I need to get rid of that 2 though, because I just want to know what 7x equals. So to get rid of a 2, a square, the opposite of a square is a square root. So that's going to get rid of my square here. So that's going to be 7x equals 6, because the square and the square root would cancel. So 7, the x is still there, and 6 is still here because this just gets rid of the square and the square root because they're inverses of each other. So 7 to the x equals 6. That's a weird one, but it's not the worst problem we've ever seen. Oh, that's it. Okay. Email me if you have questions on that, y'all.